Today there will be first Sina Ober-Blöbaum from the University of Oxford going to talk to us about variational formulations for dissipative systems.
Mm-hmm. Thanks, Miguel, for the introduction, and also thanks to the organizers having the opportunity to talk here in this nice program. It's always nice to be here, even though it's Cambridge. So the project I will talk today about is funded by the EPSRC. It's called Fractional, Variational, Integrators and Optimal Control. And the main aim of this project is to find nice modeling techniques and simulation techniques for dissipative systems. And by nice, what we have in mind, we want to do it variational. So why? Well, if we have a variational for formulation for a dynamical system, it's always, your equation of motions always are really meaningful. Yeah? So it's nice to have a variational formulation to derive an equations of motions. On the other hand, we are also interested in structure-preserving integration methods for those systems. In particular, I'm interested in variational integrators, where the base is always having a variational formulation. So that would be the second aim of this project. So this is joint work with my colleague in the Control Engineering Department, David Limbeer, and our two postdocs, Farhang Haddad-Fashi and Fernando Jimenez. And let me start with the motivation. So the system we are interested in, or the simplest system you can think of involving dissipation, is this mechanical system. Here you have mass times acceleration. We have a gradient, a potential force coming from this potential U here. So X is the state. Sometimes I also use Q as a state, so I introduced it here already. And everything in the talk now is just one-dimensional, but of course it's applicable to high dimension as well, just for simplicity. But what's important here is that we have this dissipation here that we want to model. And as denoted in this paper by Bauer, this is just a paradigmatic non-Lagrangian or non-Hamiltonian system, because there's no energy preserved. Nevertheless, we are interested in some Hamiltonization of the system, meaning we want to find a Lagrangian function, or equivalently a Hamiltonian function, which provides this equation using calculus of variations for this action principle. So there, of course, this is not a new problem, right? It's quite old, and there are a lot of different approaches how to face this problem. So one common approach is using Rayleigh dissipation functions, where you just have another function g, whose partial derivative just models the non-conservative force of your system. However, as you see, that's no action principle. Then there is some well-known work on the Canai-Caldirola oscillator, which has an additional factor, which is multiplied with the Lagrangian, and if you perform the variations and derive Euler-Lagrange equations, and assuming that this factor is 1, you just get back the dissipative system that you would like to model. However, momenta and Hamiltonian are not really physically meaningful. It's just some kind of trick. Then there is the approach based on the Lagrange principle, and that's widely used in the community of variational integrators, where you have your principle, but you enlarge it by this extra integral, which is just virtual work coming from the non-conservative force into your system. So this gives you also the correct Euler-Lagrange equation, so F could be any non-conservative force. But strictly speaking, that's not a real variational principle, right? Because you just add this virtual work here. Then there's another approach which was introduced 2013 by Galley, which is based on doubling the states dimension of your system. So you have not only a Q1, but also a Q2, and you consider a modification of Hamilton's principle, which looks like this. So you have the Lagrangian, the original one of your conservative system, then you have just a copy of that, but now you consider it in backward time, and you have an additional term which is called the generalized potential. And what is essential for this approach to get the correct equation of motions is that you have slightly different boundary conditions. So instead of having boundaries fixed, he's considering fixed boundaries at the beginning. And if you consider the varied curves, there can be different boundaries at the end. However, for both systems, they have to match, right? That you always have this path going here and back to here. If you have this assumption and derive equations of motions using the variation principle, taking variations, then in addition, you have to take in the end the physical limit that Q2 goes to Q1 to some joint Q to obtain the dissipative equation you are interested in. And there's also some recent work on this where David Martin Didier and co-authors introduced a generalized potential which looks like this, which is able to model any non-conservative force F. However, there's no real Hamiltonian that is preserved, so I think you can show that the Hamiltonian is just 0. And yeah, you have to take this physical limit in the end to get the correct equation of motion. It's not really clear what the role of the second system is. So then I'm coming closer to what we try to model this. And there was a nice work by Rive in '96 who stated that you can derive dissipative equations of motion by putting an extra fractional derivative term into your Lagrangian function, yeah, which leads to Euler-Lagrange equations of this form, where now the difference is that alpha can be a set of rational numbers. Yeah? So you consider fractional derivatives. So if you see if alpha is 0 and 1, you just get the normal Euler-Lagrange equations back. So it's some kind of generalization of the calculus of variation approach. So how are fractional derivatives derived? So that's nothing really fancy. So it's really going back to Leibniz in the 17th century, where he first wrote a letter to Hospital to tell him about fractional derivatives, right? So it's really that old already. And consider a smooth function f on this interval LB. Then there are different kind of formulations you can choose for fractional derivatives, which you can show equivalence. And we chose here the Riemann-Liouville formulation, where the minus fractional derivative, you have always a minus and the plus fractional derivative denoted here by a minus and alpha, minus and plus. And it's given by this gamma function times the derivative, time derivative of this integral, which involves here the alpha component and also, of course, the function itself. And this one is defined for alpha being in 0 and 1, and we are mainly interested in the case where alpha is equal 1/2. And why, that's what we'll see later on in the talk.
So is, I mean, does the sum there depend on the order of the sums? So if I change the order of the summation, I mean, it will probably not be absolutely convergent, right?
You mean this sum here?
Yes.
I mean, those are just the Euler-Lagrange equations you derive from the variational principle. So it depends on what kind of quotient or what kind of derivatives you have in your Lagrangian. You get this kind of
the assumption that
Euler-Lagrange
there's only finitely many non-zero
Yeah.
terms.
Ah, okay.
Yeah.
Zina, can I ask you, since we are on the slide, so there's also this Caputo
Yeah.
definition. So with this definition of fractional derivative, the derivative of a constant function is not 0, whereas with Caputo it is. So
yes,
does that matter?
it doesn't matter here right now. I mean, you can show that those two are equivalent under some assumptions.
Well, they are related.
They're related, yeah.
They are
Right.
not equivalent.
Yeah, that's true. Yeah, they are related.
Related
yeah.
is a better word.
Yeah, but at some point we have to choose for one formulation, right? But
I'm just wondering, so there are good reasons for choosing this particular.
I mean, we think it was just best practical
Okay.
from computational point of view. Okay. So, what are the properties of the fractional derivatives. So first of all, they are non-local, right? Because it depends on infinite many values of the function f. It's not a derivative, well, the product rule doesn't hold, but there are other properties which are there. So for example, you have this asymmetric integration by parts. So if you want to shift your fractional operator here to f, the sign is changing. So if you have plus, you get a minus, and if you have a minus, you get a plus. You also know if you apply the fractional derivatives with different quotients behind each other, it's just the same as having the fractional derivatives by the sum of those two parameters. And that means in particular, if you have alpha and beta equals 1/2 and take twice the minus fractional derivative, you just get your first derivative back. And for the plus, you get the minus first derivative back. What however, is not true is that you mix plus and minus derivatives, you don't get the FDT back. Yeah, that's important here. So then let me explain what Rive did. So in this paper, he just suggested this Lagrangian here, where we have the just kinetic energy, potential energy, and you have this extra fractional derivative term, which just involves the minus derivatives. And he derives the equation of motion, which leads to this term here. So here you just have the normal Euler-Lagrange equations and this extra term. What he didn't consider or didn't take into account was the asymmetric integration by parts formula. So he claimed that this equation would lead to the correct dissipative term, r times x dots. However, as we saw previously, even if you choose alpha equals 1/2, this just does not reduce to r times x dots. Yeah? So there was some slightly mistake, an important mistake in this publication. So then there were Jackie Croissant and Initian who came up with a different, they wanted to solve this problem by using something they called asymmetric fractional embedding. So what they did, they doubled the variables of your system, then perform a variation principle in this enlarged space using extra restrictions on the variations. However, the geometric meaning of the space was not totally clear, and also the restriction they chose for the variations was somehow chosen ad hoc, so there was no real interpretation behind that. However, in the end, they get the same, the correct equation of motions. So what we did something similar but also different. So we also consider two copies now of our system x and y, and we have the tangent space where we have coordinates now x, y, x dot, y dot, just the usual ones. And now we define an extra tangent space that we call T alpha r, fractional one, which involves now x and y, but also the fractional derivatives of x and y. And we choose the minus fractional derivative for x and the plus fractional derivative for y. Then we can build up the fractional phase space just by choosing the direct sum, which has now all these coordinates x, y, x dot, y dot, and the fractional derivatives for x and y. And now we want to set up a general fractional action, which involves all these coordinates. One question arises here immediately, so how are we allowed to include the plus alpha? Because it involves future values, as you can see here, for your y part. So we will still see if this will somehow violate causality of our equations of motion. That's something we will answer later on. Yes.
Sorry, I missed. So why do you have x and y? Are you assuming that you're in R2, or is this a doubling of?
Yeah, it's a doubling. So far there's no interpretation what y would be, but we will see in the end what y will be physically. Okay, now we perform the Hammond's principle. So we have fixed endpoints. We look for curves such that our action is stationary, and we take into account that we have different variations for our two curves x and y. We have to take into account the asymmetric integration by parts, also that derivative and variation change, and we consider this Lagrangian, where we have just twice the Lagrangian, just evaluated one at the curve x, one at the curve y, and we have this term which only depends on the fractional derivatives of x and y. Using all these conditions, we can derive fractional Lagrange equations, which looks like this. So again, the usual one here in black, and in red and blue, the extra term we obtain from the fractional Lagrangian parts here. So let's see what this is if we consider mechanical Lagrangians of this form, so kinetic minus potential energy. That's a term we choose for our fractional part, so it's a product of the minus x derivative and the plus y fractional derivative. And choosing alpha equals 1/2 and taking these relations into account, we end up with this system. So that's a coupled system, and it's not really that one we would like to model, right? So what we would like to model is, instead of minus ry dot, we would like to have plus rx dot here to really have dissipation. So that's not the perfect way to do it, or that's not the full story. What you have to do to obtain the correct equation of motions is to consider restricted variations. That means we consider for both curves the same variations, delta x is equals to delta y. This gives us just one critical condition, and now of course we can reorder terms in this way and just say, okay, a sufficient condition for this critical condition to hold is by setting this equal to 0 and this one equal to 0. And this leads to this equation of motion, where if we now apply alpha equals 1/2, we get here the correct form of the dissipative system we are aiming for. So what else? We get additionally this system, and now you can see that you can interpret this equation as the dissipative equation in backward time. Yeah, so there's some physical interpretation behind that. So what are the cons and the pros? So far we have only sufficient condition because we made this rearrangement of the terms. However, we get now decoupled dynamics. We obtain the linearly damped system we are interested in. We have a clear interpretation of y, namely it's x in reverse time. And if you do so, also causality is respected in the action, because future values which are involved here just became past values if you consider it in backward time. And we also get a clear Hamiltonian picture.
Why is it linearly damped in the pro? Because can you, like for example, can you do quadratically damped or other general?
I will come to this later.
But why is it pro? Why is it not a con?
It's pro just that we obtain an equation that we get.
Okay.
Before we haven't obtained the Euler-Lagrange
Okay.
equations for linear damping. But now we are able to do this. Yeah. Okay, just very briefly the Hamiltonian picture. So you have to define a fractional Legendre transformation, which not only involves the usual momenta, but also now what we call fractional momenta on a fractional cotangent space, which are just the partial derivatives with respect to the fractional derivative of x and y. Then you can set up your Hamiltonian in the usual way, the Legendre transformation times v, where v involves now all these variables minus L, which gives you this expression. And you can derive the fractional Hamiltonian equations, taking restrictions into account like this. So that's what we are used to. Here also the black one is what we're used to. We get these additional terms here. And we have an additional algebraic equation for the fractional derivatives of x and y. Now again, considering the Lagrangian we always have in mind, we get this Hamiltonian here. And you also see nicely that we get the correct dissipation terms as it should be. Yeah? So the equations are equivalent to the Euler-Lagrange equations. And we get a relation in addition between the fractional derivative of x and y and the fractional momentum. However, here the Hamiltonian is not preserved anymore. There is something which is preserved, well, it's trivially preserved, which is just the difference between h of t and h evaluated at a time point which is symmetric to the, with respect to the midpoint of the time interval. Yeah, which comes from the fact that we can interpret y as x in backward time. So that means that those two energies would cancel out. Okay, now having a clear continuous picture, we now want to construct variation integrators, and I just have one slide to explain the basics of variation integrators. So you have a discrete time, you have a discrete curve for your continuous curve, and then you set up a discrete action, being the sum of discrete Lagrangians, where the discrete Lagrangian now approximates the action on the small time interval. And for example, you can use a difference operator for approximating x dot. Then we can set up a discrete Hamilton's principle by setting this discrete action, make it stationary with fixed endpoints, which gives us these discrete Euler-Lagrange equations. And those are well known to define a flow, which is symplectic and momentum preserving. And then you can, for given 2 points, you can compute the next point, x2. So there's also a lot of work on symplectic integrators for dissipative systems, just to mention some. So this first work by Kane, Marston, Ortiz, and West is based on the Lagrange-D'Alembert principle. Then you have like the 3 works here which are based on so-called conformal Hamiltonians, where the symplectic form decays exponentially but with a constant rate. So for those systems you can even show that you preserve energy rate, the energy dissipation rate in your integrators. And then you have these works, this is called symplectic integrators. It's just called like this because for dissipative system, the phase volume slims down, so that's why they call it symplectic integrators. And that's based on the approach by Galley, where you have also the doubling system and the additional generalized potential. But if you have just general dissipative systems, at least I'm not aware of any kind of proof showing the correct energy rate of your integrators. And that's what we would like to have. Okay, now let's consider our approach here. We now have an action approximation, looks like this. So we have this LD where we want to approximate the action on this time interval. And now we have to choose a discrete approximation for the fractional derivatives. And we just chose some which were already there in the literature in this paper by Poisson and Yelizian, which is based on the Grünwald representation of the fractional derivatives. And then we have a discrete Lagrangian, which looks like this. So here we just replace the discrete fractional operators. Here we replace the derivatives by the difference operators. And what is special here now is that this discrete Lagrangian always depends on all past x, so from 0 to k plus 1, and all future y's from yk to n. So it's not like in the classical sense where your discrete Lagrangian only depends on 2 points. To make the notation more similar to standard variation integrators, we can just introduce an L stilly, which depends on x k plus 1, the same for y. And now we have extra arguments which just represent the fractional differential operators in the discrete setting. Now we can set up an action by just choosing the sum of all the discrete Lagrangian and derive, all the Lagrange equations. And we have to take into account fractional integrations by parts, and luckily there's also a discrete version for that. So if you want to shift this fractional operator over to the f, you again get a sign shift here in your fractional derivative. So taking this into account, you can show that again for restricted variations and fixed boundaries, you end up with those fractional Euler-Lagrange equations, where again the black part is the usual Euler-Lagrange equations, and the blue and the red part is what's coming from the fractional part of the Lagrangian. Now, what is different from a numerical point of view is that now for a general fractional discrete Lagrangian, you cannot solve point by point anymore. You have to solve everything simultaneously because all variables are involved. And strictly speaking, it's not really possible to define a discrete flow in this way. However, for the systems we are interested in, which are of this form, so 2 different Lagrangians and just this term which involve the fractional parts, you see that in this equation you only get the minus derivative, so you only get past points involved, and here you get the plus derivative, which only involves future points. Again, if you interpret this at backward time, which you can also do in the discrete case, this will become past points as well. And that's how it looks like. That's a standard way if you consider this kinetic minus potential energy. And then the implementation is just like for standard variation integrators. So you start with initial conditions, in particular x0 and p0. Then you solve the first x1 based on the discrete joint transformation. And here you have to also be careful in how defining them, because you have extra fractional parts in there. And then you solve the, you can solve, again, just pointwise, the discrete Euler-Lagrange equations to obtain the next xk plus 1. And this gives you all your unknown xk. Okay, so let's consider a really simple dissipative system, which is here the damped harmonic oscillator. That's your Lagrangian for the conservative system. And now we add some dissipation here. And of course, you can write down the analytic solution, which looks like this, right? So energy is dissipating here in the system. And we use a fractional integrator for different values of alpha. So what you obtain is, if you use a value alpha equals 0.5, you see that, which is the blue line, on top, which is on top on the red line, so you get the correct system back. If you use alpha which is smaller, like 0.2, you get something which is which has a higher frequency. But if you use a larger value for alpha, you get a smaller frequency here, which is a magenta curve. So we are mostly interested, of course, in the case alpha equals 1/2. However, we also tested for benchmark problems which really involve fractional terms, that we get the right solutions also for the other values for alpha. But what this picture is telling you, okay, for alpha equals 1.5, we really get our dissipative system back. And that's what you can also prove now in the discrete setting, namely that also for the discrete version, the concatenation of the minus fractional discrete operator with alpha equals 1/2 gives you this backward difference operator, which can be, of course, interpreted as an approximation of the time derivative. So that would be our fractional variational integrator for alpha equals 1/2, which just reduces to this form. And of course, that's not a brand new integrator, right? You can also derive this integrator using the Lagrange principle, where you just choose appropriate choices for your left and right forces, namely 0 for the left force, and this expression, the difference operator for the right force. So it's not that we really invent new integrators, but what's different, that we derive it from a purely variational principle. Yeah.
So if here you were using the plus definition, you will get, I guess, a progressive.
If we use the plus definition, we get a minus sign here.
Yeah, okay. And
Yeah.
then you will get xk plus 1 minus xk. Something like that.
I have to check this.
Because you look at the future.
Yeah, right, you're right. Yeah.
How will be the numerics? My question is, the numerics really are affected by using the minus or the plus? Because in the end,
No,
you're
it's the
using
same,
one.
because
Okay.
you can really show that if you use the plus derivative, you get a different equation, which is just the original equation in backward time. So if you would use the plus derivative, write down the equation, and integrate it from backwards forward, you would get the same. Okay, so just some standard comparisons. So we have here first order integrators, so we compared also with first order implicit and explicit Euler methods. And it's not really a surprise, because it's already seen for also D'Alembert integrators, that energy is, the energy rate is much nicer preserved for our fractional integrator, where the implicit just underestimate the energy and the explicit overestimates the energy. So that's where we are right now. We can also do it for, of course, nonlinear system. It doesn't have to be linear, of course, because the Lagrangian L was just anything. And here you also a comparison with the Euler methods show that energy decay for the fractional is much nicer preserved compared to the Euler methods. And also for damped systems, like for the Dampf-Kepler problem, you can identify new invariants. You don't have the same invariants anymore as before, like angular momentum, but you can define related invariants which are exactly preserved by our integrator here. Okay, so summing up the fractional part here, what we can and what we cannot do. So first of all, we can do nonlinear systems with linear dissipation. You saw that. We can also do nonlinear systems with fractional dissipation. So if you don't choose alpha equals 1/2, you would get some fractional damping, which is linear in this fractional derivative, and which is also in applications used, for example, to model material parameters or material properties, especially in engineering applications. So that's something we can do. We get a clear Hamiltonian picture. However, we cannot yet find a meaningful conserved quantity, so the Hamiltonian we derived is not conserved. And we also weren't able so far to do nonlinear dissipation with this approach. Yeah, that's a little bit of a pity. So in parallel, we also worked on an alternative approach in this project, which I want to present you right now, which has nothing to do yet with fractional derivatives. And it's based on embedding the non-conservative system in a larger conservative system, which is of course also not a new idea, which was done in many different situations, also in quantum mechanics. And one famous example is the Caldera-Regget model, where you have a closed system consisting of the Lagrangian of 1 degree of freedom oscillator. Then you have a heat bath, which is modeled by n-harmonic oscillators in this way, and you have some coupling dynamics between heat bath and oscillator. And then you can derive the Euler-Lagrange equations, so that's the equation for the oscillator, that's for the heat bath, and well, that's just linear equations, so you can somehow eliminate the heat bath by finding an analytic solution for this and plugging it back into the oscillator equation, taking some limits and take some technical things into account, you end up with this Langeville equation, which describes a noise-driven system with damping. Yeah, that's the important part. It includes damping, although the closed system is conservative. Yeah, and that's the main idea. You somehow enlarge your environment of your system. And we don't use these heat baths. Instead, we use some approach called the transmission line, and we are mainly interested in those two situations. Here we have just an oscillator where we have a damper here, and here we have a dual oscillator system with a damper in between, which gives us those two damping forces. So for the first one, it's also well known, and that's what is called Rubin model, that you can equivalently define a system where you replace the damper by this transmission line, which is comprising springs and masses. Yeah, so what's happening here, so the energy is dissipated here and goes into the transmission line, so it's just transferred in there. And as long if this wave is not reflected and coming back here, and you just consider this oscillator system, it looks like a dissipative system. Of course, only until this wave coming back here. But if you just choose the line long enough, right, you will always end up with a dissipative system. However, this approach does not work for this dual oscillator system. In the end, if you do the derivations, you just see that you don't get the correct equation of motions back. And one reason is that the transmission line is not grounded here somehow to some inertial flame, as it is here on this part. So we came up with a different inertial line, a different transmission line, namely which consists of so-called inerters. And that's an element which is really nicely explained in this paper here by Smith in 2002, which is a real dual of a spring and it was mainly also used to find connections between electrical circuits and mechanical systems. I don't want to go into too much detail, but what is important is how is the inertia defined. Well, it's defined by the inertia forces, which are always proportional to the relative acceleration between their terminals. So here each inertia is connected to this mass, the big mass Q naught, and that are the forces which are acting in the system with some inertance B. And the kinetic energy stored in each inertia is given by the relative velocity squared times B over 2. And now we want to set up the Lagrangian for the system. So here we have just the kinetic energy of the two oscillators, potential energy of the two oscillators. That's the inertia kinetic energy, and the energy from the springs of the transmission line. And we obtain those equations of motion for the first oscillator, for the second, where here we just have the spring force coming from the very first spring of the transmission line, and we have the force of the very last spring, because that's connected to the second oscillator, and the inertia forces. And that's the equation of motion for the transmission line. So now you can plug in those equations in here, and what you get, and that's what we would like to see, is that we just have the influence of the spring force of the first spring, which acts on the dual of the second mass, on the second mass. Considering now we do something similar as for the heat bath approach. So we just take the limit where n goes to infinity with a fixed length. So this gives you this Lagrangian, which is now space distributed, and we have a displacement denoted by q of xt, where q of 0t is just the first mass, my oscillator mass, and q naught is still the last mass of your system. And now you still have kinetic and potential energy for your two oscillators, and now you have this kinetic energy for your string that you approximate by this limit, and you have the deformation energy of the spring, where the density parameters rho and the stiffness parameter are given by the inertance and the spring constant we had before. And then you can derive equations of motion again by also substituting the wave equation back, which gives you this for the first oscillator, where we now have this tangent force, which comes from the left boundary of the string, and the same tangent force with negative sign, which is acting on the oscillator, the second oscillator. And we have this additional wave equation for the string. And now, well, we claim that this model we have here is nothing else than a dissipative system if you consider our simulation time, which is short enough. And first we tested it numerically. So we have these two systems, the open oscillator system with the damper and the closed oscillator system with the transmission line. We have to be careful how initializing the transmission line system, because we have to have the same energies in the system in the beginning. And here you see the displacement of the second oscillator and the velocity of the first oscillator, and the curves of the two approaches lie on top of each other, so you don't really see a difference here numerically. But of course that's also something you can prove. But first here you see so this is displacement and time, and that's the deformation of the string. And you see how this wave evolves, and then if it bounces back at the very end of the transmission line and comes back, you won't see the effect of dissipation anymore. But as long as it's not coming back to x equals 0, you will always see a dissipative system, and this line here is exactly what you will see for your open oscillator system. Okay, this can also be proven. So if you have a spatially distributed version of the transmission line, you have the following properties. First of all, the displacement wave propagation velocity is given by square root of k over rho. Then you can characterize the damping factor given by this expression, and you can show that the open oscillator system is described by the same set of differential equations as the closed transmission line system prior to the arrival of the inward traveling wave. yeah, which is given just by 2 times the line over the propagation velocity. And the proof is based on the fact that we know how the solution of the wave equation looks like. So we take the D'Alembert form, which involves the outward and inward traveling wave, and additionally the Q naught of t, because we have a slightly modified wave equation. We take derivatives, space and time, and plug it into the wave equation, and we obtain back our propagation velocity, which we claimed. And similarly, you can now, you can model this tangent force or substitute this tangent force by taking also space and time derivatives, replacing the plus wave by in terms of all the other terms here, and then express everything in terms of the time derivatives of the incoming wave and of the oscillator systems. And if you assume that the reflecting wave hasn't been come back, you can just neglect this term, and you end up with this expression, which is the same as that expression, and which is just the damping of our system we are interested in with this damping parameter. And of course, you can do the same also for the second oscillator, where we just have negative sign and then the correct damping force that we would like to have. Okay, what about the energy? So energy, what you can also show that energy absorbed by the transmission line is equal to the energy which is dissipated in the damper. And it can also be expressed in terms of this quadratic form here, only depending on the initial conditions and the matrix W, where W solves the Lagrangian equation. And what you can also say that the closed system stored energy is also a symmetry of the open oscillator system. Yeah, just because the two systems are equivalent for a given integration time. And the total energy is given either by the initial energy or equivalently by all the energy which is transferred to the transmission line, which you also compute in terms of the quadratic form where W is now the limit of W of t, where W was solving the algebraic Lagrangian equation. Okay. Now we can do the same in the discrete world, so we just choose some kind of approximation for the discrete Lagrangian. Here the really simplest one where we take difference operator for the velocities and left point evaluation for our states, for our configuration, and derive discrete Euler-Lagrange equations, where we get here the discrete version of these spring forces, and we obtain a space-time discretized wave equation, which looks like this. And then we get the same results. Of course, it's not really straightforward. Well, it looks straightforward, but the devil is in the detail, of course. We have the same propagation velocity. We have the same damping factor, and you can also show for the discrete systems that prior to the inward traveling wave arriving, the variational discretized dual oscillator system is equivalent to the variational discretized transmission line system. And the proof is similar, right? It's based on the discrete D'Alembert solution for the discretized wave equation. Again, this is then the discrete reducer system you obtain, and we see the same integrator we had before, right? It's some backward difference operator to approximate the velocities. Similar results for the discrete energy. So the discrete energy of the transfer to the transmission line up to time j is the same as the energy dissipated in the damper. And this can also be expressed in terms of this quadratic form where WD now solves a discrete time Lagrangian equation. So generally what you can say about energy, where from backward error analysis we know that the total closed system energy is almost conserved, meaning the error is bounded over exponentially long time intervals. And that's not only for the closed system we started with, but also for the open system scheme. So we know if we use this dissipative system for this dissipative integrator for this dissipative system, we know that we have some energy which is preserved, which is not the total energy. This expects better energy decay prediction using this integrator compared to non-variational schemes. However, you cannot really say something about the energy rates dissipation rate because the total energy consists of these two terms, the oscillator energy and the dissipation energy, and maybe there might be errors in one rate which will cancel out by errors in the other rate. So that's something not clear yet now. However, you can at least do some computations for this case where we compare the energy in the transmission line based on the expression we got with the Lyapunov equation, where you know that the total energy transferred to the transmission line is given by those expressions. So you can do this, of course, for the continuous and the discrete system. And what we see with our approach is that the line energy, of course, first starts at 0, and you get a much nicer approximation for our variation integrator, which is of 2 orders magnitude lower compared for non-variational integrators. But still something that has to be proven. Okay, what we can also do with this approach is nonlinear dissipation, namely dissipation of this form, where the parameter, the constant, is replaced by a function which is separable in Q and Q dots. And this then maps to velocity-dependent inertors and displacement-dependent springs. And you have to take more techniques into account. First of all, you are faced with mechanics, with system containing state-dependent springs or masses. And also, we get a nonlinear wave equation in the end that you have to handle somehow. And that's just recently submitted in those 2 papers here. Let me conclude. I presented a purely variational formulation for dissipative systems. The first one was based on fractional derivatives defined on an alpha fractional phase space, where you obtain this restricted fractional Euler-Lagrange equations, and for alpha equals 1/2, you get the correct linear dissipative systems. And the second approach, called the transmission line approach, embeds the system into a larger conservative system, and by something, which we call wave reduction, because we just take the solution of the wave equation and plug it back, you obtain also a dissipative system, which also allows for nonlinear dissipation. Both discrete versions leads to well-known structure-preserving schemes. However, the main point I want to raise here is that it's derived purely variational. And in the future work, we are really interested in proofs that energy rates are really preserved based on those 2 approaches. And we are also working on higher order schemes, where especially for the fractional part, it's interesting how quadrature rules of the Lagrangian and quadrature rules you have to choose to approximate the fractional derivative, because it's also integral, how this comes together to what kind of higher order schemes. And we are also working on optimal control applications on this. Okay, then thank you very much.
We are running a little behind, but I think we can allow for a question or 2 still. Yes, Ari?
Is this method that you wrote down the same as the symplectic Euler method?
Well, I mean, you mean in absence of dissipation?
No, with dissipation.
I mean, if you don't have the dissipation, you get the symplectic Euler, right? That means, it means how you define dissipation in the symplectic Euler method.
We can define the symplectic Euler method for any partition ODE, so you can define it even for a dissipative system. Is it not the same method?
It really depends on how the dissipation for the symplectic Euler method is modeled.
Talk about it.
I think what you mean is a splitting method, not a symplectic method.
It's not symplectic then.
Oh, well, it's not actually. Well, okay.
The usual
The lowest order Lobato 3A 3B method.
Well, we have another question here.
Yeah, so it's a very naive question. You can double the order just by enforcing the ODE with the Lagrange multiplier, right?
Sorry?
You can double the order just by enforcing the ODE by the Lagrange multiplier. So how does that fit in with all this?
Okay, the order of what exactly?
So you just multiply the ODE by Lagrange multiplier, and that becomes your variation statement.
By Lagrange multiplier.
Yeah.
totally different other set of equations.
Yeah, I know, but I was trying to understand if there was a
Yeah.
relationship.
Then I'm not totally aware of that. So you're saying your Lagrange equations you multiply with the Lagrange multiplier,
Yeah.
and then you obtain dissipative equations.
Yeah, you do.
Yeah, so the entire variational statement is the constraint. So you
Oh, you
don't
mean
have the
the
normal bit.
restrictions?
So your L is Lagrange multiplier times the ODE. So differentiating with respect to the Lagrange multiplier, you get your ODE
Yes,
back.
yeah.
Differentiating with the
Oh, you
dependent
mean I just take the dissipative equation, take the Lagrange multiplier, and then, okay.
So with the heat equation, your other
You get the
your other
backward heat
equation is the
equation.
backward heat
Yeah.
equation. So it relates like that, and it's going the wrong way. But in fact, the other set of equations are linear,
Here.
and they're really quite different. I was doing some examples in my head just about I was listening to talk, and I think it's really very different. Yeah.
Okay, let's thank the speaker again and hope that